So, good morning, ladies and gentlemen. So, my name is Hayato Tsuji. I'm an associate professor at the University of Tokyo. So, I'm the moderator of this morning's first session. So, the speaker of this session is Professor Ei-ichi NEGISHI. He's H.C. Brown Distinguished Professor at the Purdue University. And, of course, he's a Nobel Laureate in chemistry in 2010. Let me briefly introduce Professor Negishi. Professor Negishi, he graduated from the University of Tokyo in 1958 and joined the Teijin Company. And in 1963, he received his PhD degree from the University of Pennsylvania, and he spent several years as a postdoc and the assistant to Professor Herbert Brown in Purdue University. And in 1972, he was appointed as an assistant professor in Syracuse University in the United States, and afterwards promoted to the associate professor. In 1979, he went back to Purdue University as a full professor, and since 1999, he is a H.C. Brown Distinguished Professor. Okay, so today his talk will be related to the palladium catalyst cross-coupling reaction, and the title is Tandem ZACA Palladium Catalyst Cross-Coupling as Widely Appreciated and Selectively Route to Chiral Organic Compounds. So, Professor Negishi, please.
Thank you very much. Well, thank you very much, Dr. Tsuji, for kind introduction, and I'd like to thank all the organizers for staging such a wonderful meeting, which I'm enjoying very much. And I thank you all for coming early in the morning to listen to our talks. What I would like to do today is to sort of reminisce my career, which fortunately led to 2010 Nobel Prize, and then hopefully in the latter half of my talk, I'd like to spend some time in discussing what we are currently doing. So, they are represented by these two, red and the blue part, the red one first. And as stated in the introduction, I went to here, where am I? In Japan, that doesn't matter. To United States on so-called Fulbright Smith-Munt all-expense scholarship. It was a wonderful thing. Only thing was that success ratio was 1 in anywhere from between 50 to 100. So I was lucky. But more than that, I learned most everything at the professional level, the foundation and the beyond in America. So though I am a Japanese, I am American-made, U.S.-made chemist, I should say, and I'm an organic chemist. And I want you to look around, in this room. Of course, there are some inorganic steel frames and so on, but many of them, I shouldn't say most, but many of them are also organic. First of all, we ourselves are organic. What we wear are organic, predominantly, and what we eat, predominantly organic. We need some minerals, but mostly organic. And if you look at this, organic, we need organic items. What that means is that we need organic synthesis, and there is a prediction probably truthful, even though despite the declining birth rate in advanced nations, the world population is still steadily increasing. Pretty soon it will be doubled. Then at that rate, soon the mankind will need another planet to grow our food items, collect our food items, and, all the other things, more and more of all the other things. So what could be alternate solutions? In my mind, there is no question that we need to chemically prepare, synthesize. Hopefully not so much food items. I like the taste of Japanese food and French food, Italian food. They are organic, but not synthetic. And we need to do a lot more synthesis. But I am convinced that there has been a wonderful revolution during the last century. Professor Noyori was touching on the significance of the discovery of nylon. I agree fully. So nylon very well replaced silk. Of course, silk has is said to have a better sort of touch and other subtle items. But nylon has replaced the silk, ladies' silk stocking, and so on and so forth. Parachute. And then came dacron or polyester. This, my dress made by my former company, Teijin, is 100% polyester. It can be recycled, melt again, and then spin again, and so on. The nice thing about this is that you don't need ironing. I have never ironed this thing for almost a year. Still, I see a crease. And my shirt, 50% cotton, 50% polyester. I like 100% cotton shirt, but I wouldn't wear during my trips anyway. Anyway, so here you can see the replacement of naturally obtained natural fiber materials with synthetic, chemically synthesized polymeric materials. And I'm now back to that company as a consultant. I recently learned that worldwide, synthetic materials outweigh, in volume, sales, and amount, far outweigh now the natural material. So this is the triumph, in a way, of synthetic organic chemistry. So when I went to University of Pennsylvania in 1960, I had a very weak background in organic synthesis, I must confess. But the curriculum there was superb. And I began learning organic synthesis from ground floor up. And then I noticed how should we further improve the art of organic synthesis. And at that time, I noticed that organic compounds are, let me see, how do you advance this thing? Oh, here. Thank you. Organic compounds mainly consist of these green, about 10 or so shown, organic kinds of elements. And 50, 60, 100 years ago, most of the organic compounds have been sort of synthesized by sort of playing with these compounds, chemicals containing these compounds. Maybe a little bit of alkali metals. Then came 100 years ago, as you know, 1912. Of course, that's the year that Victor Grignard and Paul Sabatier won the Nobel Prize. This year we are celebrating their centennial anniversary of their winning the Nobel Prize. For the first time in the area of organometallic chemistry. The Grignard, of course, introduced the magnesium as a significant metal. Sabatier introduced catalytic process. Grignard chemistry was predominantly or almost exclusively stoichiometric. Sabatier introduced D-block transition metals as a catalyst in catalytic hydrogenation, mainly using nickel. So as I learned all these things, I realized that there are more than 100 elements in the periodic table. We shouldn't be just confining ourselves to the use of these 10 or dozen organic elements, of course. Then I realized that there are several different kinds of metals. And I quickly learned that many of them, the heavy ones, red ones, they are intrinsically radioactive. It's very difficult to use them in organic synthesis. There are 26 of them shown here. So we take away those for the moment, including technetium. And there are some intrinsically toxic ones. All Japanese know how toxic cadmium is. This causes itai bio, and then you develop a bone ache, so much so that you would rather die. Of course, we Japanese know how toxic mercury is in Minamata disease. And pretty much in almost any form of mercury can appear to be toxic. There's thallium, lead, tin, arsenic, beryllium. I think these are the kinds of elements that we probably shouldn't use. Maybe the tin has been used in cross-coupling, but I caution you that its use should be done with the greatest precaution. Okay, so we take away those. And then, of course, inert gases. By the time you eliminate these kinds of elements, you're left with about 70. Still, you're left with 70 elements. A lot larger, almost an order of magnitude larger than organic kinds of element collectively. And so 70 and 10 organic elements plus about 60 metals. Where are those 60 metals? There are these blue ones, about 20 of them, so-called main group metals. They are relatively cheap. They're relatively safe, by and large, except for some of these. And we get to use about 20 of them. And then, but what I want to emphasize today is the one in the middle, 3 times 8 minus 1, 23 D-block transition metals. They are wonderful metals because they can be used as very useful materials. Look at them. Titanium, in the aviation industry. Iron, of course, iron all over. With chromium and nickel, you have stainless steel, gold, silver, copper, the kinds of metals that we like to have, platinum, iridium, and so on. But today, what I want to emphasize today is their ability to serve as wonderful catalysts. These are the kinds of elements, metals, that we really need in this century and beyond, because they catalyze all kinds of reactions. And by catalysis, we mean they must go around and around and around. So fundamentally, they will not be lost. Of course, in practice, we lose them little by little. But as I will tell you, in our palladium catalyzed cross-coupling, we tested many representative cases, and in all cases tested, we exceeded turnover number of million. So million or more. So even if they cost $1 million per mole, I'm sorry, I'm using it, our million yen is also okay. Doesn't matter. $1 million per mole, it's only $1 a mole, for producing 1 mole of the desired product. And then someone said, well, for toxicity reasons, palladium is associated with a mild toxicity. So for preparing drugs and so on, we would like to go further. We would like to use less. Okay. So we went back and tested. Analytical method can be very tricky. But not in all cases we tested, but in many cases, we were able to go not just 1 million, 10 million, 100 million, billion, 10 to the ninth. Then my friends told me that at that level, you don't need to worry about the toxicity anymore. Even the presence of that small amount of toxic material won't cause hardly any major damage. Okay, anyway, so these are the ones which I am saying their catalytic actions will help us sustain our world and then probably promote, make our livings more prosperous. And I really believe that. That's one of my key messages today. And of course, at the top of my list, there is a catalytic reduction of CO2. Many people, many society, majority of people today say we shouldn't produce so much CO2. True. Well, I'm not sure. And then some will bury CO2 as it's sold. That seems to me they are going in the wrong direction. CO2 is one of the main starting materials for all the important organic compounds that we have talked about. So we shouldn't be afraid of producing CO2, provided that we can catalytically recycle into a useful material. We need to reduce CO2 from +4 to any level, +3, +2, +1, 0, -1, -2, -3, -4. Methane. Any level is useful, as long as we do it economically and catalytically. Okay, we can reduce it easily. 100 years ago, Grenier told us, treat CO2 with a Grenier reagent. Then you get the carboxylic acid, in which that carbon is +3. Carboxylic acid, oil, fat, useful, nutritious, but not economical. Okay, so let's take a look at what kind of reactions are needed. Okay, here it is. Many people say, Negishi, Suzuki, cross-coupling chemistry is not very green because they use organometal. instead of using CH hydrocarbon. I say, wait a minute, give us a break. If you think about what metals do in our cross-coupling, many things. First of all, carbon-metal bonds intrinsically more reactive. Secondly, metal halide formation as a byproduct, they will all but assure that the reaction is downhill, thermodynamic sink. Kinetic acceleration, thermodynamic sink. Thirdly, metals can serve as very good, along with halogen, regio and stereo markers. And I'll show you that in our cross-coupling synthesis via cross-coupling, we get pure. By that I mean greater than 98, 99% pure. In other words, we don't see any other isomers. Okay. So the markers. And then I say, if you use CH compound, which are allegedly greener, which I don't think is the case in most cases anyway, you generate HX via coupling. That's an acid. Now, to neutralize that acid, you use a base. So, I think all these things must be compared in overall sense. In overall sense, I believe our approach is, in most cases, greener. So, here's my definition of green chemistry. How to synthesize any organic compound. In high yield, Y. Efficiently, E. Selectively, S. YES. Yes! Okay. A la Barack Obama. It's getting to be a little old, but he's maybe saying the same thing again. Anyway, so, and I'd like to add two more things. Economically, of course, very, very important. And safely, which I touched on a moment ago. YES. I wanted to have a second Y, but nobody has given me the second Y, the Y word that I can use gladly. Okay. And as I was telling you, my notion, which I conceived of as a beginning graduate student, was, well, let's consider all usable elements. There are about 70 of them. Why should we just limit ourselves to a dozen or two? So I touched on this one, avoid radioactive and inert and inherently toxic elements. But then I thought, 70? Only 70? Many people said, wow, what are you doing? When I was an assistant professor, you are just using all over, all kinds of elements and messing up just the organic synthesis. But I say 70 was not a large number. I thought it was a frustratingly small number. Then it occurred to me that maybe we should start considering there are binary combination, at least metal, 60 of them. Then you get to have an exponentially high number, 3,600 or close to 5,000. And I called this 2 is better than 1 principle. 2 is better than 1 principle. Then later, I realized that this 2 is better than 1 principle operates in chemistry here and there. I will show you how to generate very strong acids, which are, of course, acids can induce many reactions. And then you notice that in the Ziegler-Natta polymerization, they use aluminum-titanium combination to generate a superacid, actually, effectively. And this concept I thought it was mine, But no way. Several years before me, George Olah already had a wonderful Angewandte Chemie review article in which he was clearly delineating this 2 is better than 1 principle. So I want you to keep this in mind. And of course, when we use 2, we use relatively cheap metals, inexpensive metal, as part of RM, and then perhaps transition metals mainly as catalysts. Okay, so I went through this, and here, of course, we learned all these things from Mendeleev. I saw this in St. Petersburg, or Sankt Petersburg, which, however you call. It looks more like this. I saw it as I attended the international symposium there. I was taking a bus every day, and one day I noticed this thing. What is that? Of course, I knew what that was. And I figured it must be a Mendeleev Institute. So after returning hotel, I walked back, walking almost 1 hour. And of course, this is still not fully explored, as you know. But this is our universe, chemical world. Or you might say our ballpark. And we might as well use all of them. Then, as a graduate student, I tried to think, what would be the most widely applicable methods for organic synthesis, mainly for carbon-carbon bond formation? And I came up with this notion that we should do it in Lego game fashion. 2 pieces, one with a hole, the other one with a stick, and then you just snap them. And then if you can do that, you go through retrosynthetic analysis, and no matter how complex your target molecules are, one by one you start chopping them, and then you just reverse that process. That's basically what the Woodward and E.J. Corey, and more recently K.C. Nicolau and Kishi and others have been showing. And of course, if you mix Grignard reagents with organic halides without catalyst, you can form the desired organic compound, R1, R2, by this Lego game approach. But the scope is awfully limited. When these are unsaturated group, aryl, alkynyl, alkynyl, they hardly work. There are some way getting around it, but I paint this territory red. When they are alkyl, like this, or acyl, your chance is higher. Your chance of success is higher. But there are all kinds of problems here again. Many people are trying to improve this thing. But I painted the whole thing yellow. And more recently, we were able to present this. So for the same chart, now with the palladium as a catalyst. More than half of the boxes are now green. I can paint green. We still have some problem here. And many excellent younger researchers are improving. But then I realized that we can get the same kind of product by alkylation here. Instead of doing this, we do this. So, especially with the copper as a catalyst, or nickel. Anyway, there is smack in the middle, 3x3 matrix. no matter how we do it, they gave us a problem. And here again, I said, let's give up. Instead of hooking these two kinds of nasty, capricious groups together, we shift the point of CC bond formation by one position, do this. They are wonderful. So I will be using, towards the end of my lecture today, some of these. But why metals? Well, of course, you know that if you mix alkane and alkene, hardly anything happens under mild conditions. But if you convert this or if you replace this with a carbocations with an empty orbital, then they react very readily, if wildly. But I want you to compare this carbocations with a borane. They are isoelectronic or whatever, however you call. And sure enough, this reaction proceeds very readily, even at minus 50, in many cases, minus 78 degrees. And looks like they both proceed by similar mechanisms. And if you accept that, then you can readily understand, and you can predict, in fact, it's too late for you to discover this reaction. It's been already discovered. But this is the hydrozirconation, wonderful reaction that we use quite frequently. Bottom line is generate these kinds of species, then you are in business. But then there is this seemingly mysterious phenomena. In other words, if you mix acid and base, Lewis acid and Lewis base, they should bang couple to form this species. But in other words, with Grignard reagent and then organic halide, many times they don't react very well. The problem appears to be kinetic. And I was sensing, but I wasn't quite understanding. But until I found this paper in a fairly reputed journal, you might say, and also surprisingly recently. If you look at this situation, as this pair of electrons being transferred from B to A, then a positive charge develops here. That positive charge will start attracting back. A, as it begins to receive a pair of electrons from B, then a negative charge develops here, and then that will start repelling the incoming electron pair. So this polarization acts as a barrier raising effect, which is shown here. So, in other words, this simple acid-base reaction, in general, there is a problem. So how to overcome? Of course, the answer was already there back in around 1950. The notion of this synergistic bonding, in other words, 4-electron process, not a 2-electron process, based on this Fukui's frontier orbital theory. So all these are frontier orbitals. So in the middle, there is this acid-base interaction that I was talking about. Alone, this must have some high barrier, kinetic barrier. But in this synergistic bonding scheme, there's this back donation. In other words, 2 electrons from dehybridized orbitals of the transition metals, for instance, can be back donated. So the polarization effect can be minimized or essentially nullified. So this 4-electron two-way processes must be kinetically very favorable, and no wonder this thing reacts very rapidly. Palladium reacts very well, very rapidly with alkenes and alkynes and arene. No wonder the scope is very high, broad. But if you accept this dual synergistic bonding scheme, I think this is a very crucial point in my research career. Then you should also accept this hydrometallation. In other words, here, this part, this part, this part, all the same as this. All you need to do is just to replace this dehybridized non-bonding, the orbital with the sigma orbital like this. Then this is also a 4-electron kind of synergistic concerted process for variety of hydrometallation reaction. No wonder they are so fast in many cases. And then they add strictly, essentially all of them add essentially 100% cis addition, H and hydrogen from the same side. You can take advantage of the products because your palladium catalyzed cross-coupling is waiting. That process is very, very, how should I say, faithful. So they will just snap without messing up any part of the molecule. Just snap to it. Okay, and then if you accept this scheme, synergistic bonding scheme, you can replace this hydrogen with a carbon sp hybridized orbital. Then it should still be the same kind of process constructed. This, in my opinion, is ubiquitous or broadly applicable mechanism for various carbometallation. This area may still be a little bit open for young people to get in. This one is pretty full. But we have managed to discover a few to several of our own based on this simple notion. And of course, the pioneer on this matter is Karl Ziegler, Germany. Accidentally they had a small amount of titanium chloride, I understand, as a contaminant or impurity that served as a wonderful catalyst. But as I said, our ballpark is a periodic table. We've covered hydrogen, we covered carbon. We still have almost 70 other elements. Why not? So we can put so-called heteroatoms. They tend to be more electronegative, like a halogen and sulfur and so on. And by the time you bring them, as soon as you bring them, then you have to worry about the thermodynamics. Maybe at one point or another, reactions may become contra-thermodynamic. As I was emphasizing, formation of metal X drives the cross-coupling reaction in one direction. But now you are starting with MX bonded species. And that is true. But still, as early as 1960 or so, 65, Mike Lappert in the UK reported a wonderful haloboration. Boron is pretty electronegative, so we're lucky. Haloboration. And you're right. This reaction, too, is essentially 100% syn addition, as dictated by this scheme, predicted by this scheme. And a scope of this heterometallation may be limited by the factor that I just discussed. Now we are busy exploring all kinds of metallometallation. There are 60 or so metals that we can play with. And we are indeed finding some of them already. And leave us some room for playing, but you're welcome to get in. So, and when I discussed 2 is better than 1 principle, if you mix 2 coordinatively unsaturated species, they like to do this, as you know, to plug up the empty orbital. In so doing, they can also may go through this or may end up with this one, or they may exchange. That's the mechanism for transmetallation, as you know. But here I want to point out to you that this one, in other words, one bond is still there, but the other one is cleaved. They're just going through all kinds of processes like this. And look at this thing. Well, of course, Lewis acidity here at M1 is restored, but now this Lewis acid is right next to this dipole with a positive end closer to it than the negative end. This, I believe, is one of the main reasons why species like this can be super acidic. They are more acidic than this by a factor of 10 to the 10s, 10 to the 15s, 10 to the 20s, or maybe even beyond. So this is one of the main reasons why we want to consider the bimetallic systems. Okay, so now I have told you that we have come up with, we and others, I should say, probably the very widely applicable reaction, which will probably become the most widely applicable CC bond or organic synthetic reaction ever, possibly surpassing, hopefully, Grignard chemistry. And in my group, we did a comparative study, and as you can see, palladium significantly better in selectivity than nickel. And I just show you quickly. Well, here we did this 2-week experiment with Tony King. Here, in this case, we were comparing this efficacy of the metal in this position, Rm, lithium, sodium, magnesium, zinc, mercury, boron, aluminum, which was done in 77, published in 78. And out came zinc, which later became known as Negishi coupling. But we did them all. Out came boron, which later was labeled as a Suzuki coupling. Out came tin, became steric coupling. So exercise like this, which we did in maybe mere 2 weeks, very useful. Turnover number, million and over. And here I want to show you, because I want to discuss one more reaction very quickly. But as you can see, we can synthesize all kinds of complex structures with, so here I show greater than 98% pure. They are formed pure. Okay, of course there are some byproducts, salt and other byproducts maybe, because the yield is not 100%. But isomeric purity is throughout. You don't see any other cases. By cross-coupling, you preserve all the delicate features, stereo and regio chemistry of your intermediate, and then you get pure all the way through. Here again. So let me quickly show you. Okay, so here 4 dienoate, high yield, essentially 100% purity within the detection level. Here we recently made all 8 possible isomers of a trienoate. And I just want you to scan through this yield of the final palladium catalyzed cross-coupling, and then isomeric purity of the crude product, okay, with crude product. Okay? Yield. And, this is an intermediate. So once you make this intermediate pure, then by hydroboration here, then you get your products isomerically pure. And the final two were the most challenging, but in the end, there was no issue, no problem. So once we make them intermediates pure, then high yield, and essentially 100% isomeric purity. So I don't have time, and in the last 10 minutes or so, as promised in the title, I want to show you how we make alkanes, aliphatic, the saturated compounds like this, with the control of absolute stereochemistry. And for this, we needed to discover this reaction, alkene and carboalumination. You might say this is a one-step Ziegler-Natta polymerization. I think that's right. Okay, one-step Ziegler-Natta polymerization. Or Kaminsky version, because we use zirconium. And you might think that it is a lot easier than Ziegler-Natta polymerization, but that's not quite true. It took us 17 long years to come up with this thing. Patience and tenacity here paid off. And, of course, the brilliant mind of Denis Kondakov, talent of Denis Kondakov, who originally came from, where else? St. Petersburg. Anyway, so here yields are okay. The E is anything above 70% E is usable, but we like to have 80%, in other words, 90-10 mixture or higher. Okay. In most cases, we can attain that. Now you go from here to here. So what? Well, I want you to note that here I only show R1, any kind of carbon group, with or without functional groups. So these are called substrates of one-point binding. And in the previous major development, sharpless epoxidation, you need allyl alcohol, Noyori catalytic hydrogenation, you need allyl alcohol and the like. In other words, substrates of two-point binding, proximal heterofunctionality guiding the introduction, approach of the reagent. We don't need that. So this is a substrate of one-point binding. And I think that much, this kind of reaction is that much more flexible. And then the best catalyst we borrow even now. And we are in the process of coming up with a better one for higher turnover number, borrowed from Gerhard Ecker, who reported this in a timely fashion. 1993, 1995, we had a major success. And one of the dangerous side reaction is this cyclization process. And here, starting from here, this is what we want. But if you don't have a bulky enough ligand here, reaction goes through this, and then no fun. Or if you have this one is a Ziegler-Natta polymerization of Kaminsky version, but this has never been a serious problem for us because they need a so-called MAO, the promoter, polymerization promoter, whopping amount, 1,000 to 1. something like 1,000 to 1, something like that, promoter to catalyst ratio. But much more dangerous is the cyclic processes. These processes are relative to olefin metathesis reactions of Grabson, Schrock, and so on. And these transition metal compounds, they like to do this, and that's not good. Well, some people have made some use of this one, like Hoveyda, Whitby, Mori, and others. But practically, you can only introduce ethyl nicely. Scope is very, very limited. And to avoid these cyclic processes, we needed to use aluminum. Aluminum is of moderate reactivity. It doesn't overly alkylate. If you use Grignard reagents like they do, then it will doubly, triply alkylate, and then they start talking each other, and then the net result is a cyclic reaction. Okay, I don't have time to go through this thing, but I want to show you one cute example which you might like. Here. This compound is called the acid component of praying gland wax of gray lag goose. Answer. Goose, they fly over Siberia at a channel from Siberia to Hokkaido, back and forth. They must fly 1,000 kilometers or 2,000 kilometers. I don't know how long. Presumably it's a very, very fine grease down here. But it was prepared once before us in 20 steps, overall yield 1%. It was a brilliant synthesis, I thought. But when we analyzed, then these are the two numbers that I got. Okay, even if it is a super grease, in 1% overall yield, going through 20 steps, you cannot make money. So I'm not sure if we can make money now, but show you what we have done. Oops, it went too far. 10 steps. 10 steps is a lot better than 20 steps, believe me. And 12% overall yield is a lot better than 1%. I have not thought about making money based on this yet, but someone else might, with some more improvement. In other words, so this thing is approaching being practical, in my opinion. So here we start with aryl alcohol. It's just substrate of 2-point binding, but never mind. So you add methyl and aluminum. Aluminum is iodinated. So this one is packed with chirality and the functional group. Okay, now you have this isoalkyl iodide. We lithiate, zincate, and vinylate. We go that way instead of using this one as such. So in 2 steps, you go from here to here. And this thing is about 82% EE, 90-10-ish mixture, obtainable in reasonably high yield. So after 1-2, we call that asymmetric carboalumination zirconium catalyzed asymmetric carboalumination of alkenes. Zaka reaction. Zaka. So now you're ready for Zaka. After first one, you do a vinylation like this, and then you do the second Zaka and the vinylation, the third Zaka. So this is the second one, third one, fourth one. After the fourth one, you oxidize, and then you get this alcohol. So in 1, 2, 3, 4, 5 steps, you're here. And then if you check this thing by NMR, it is a 9 to 1 to 1 to 1 to 1 mixture. What is 9? 9 is what is shown here. 1 to 1 to 1 to 1. That's a single site epimer. There are 4 chiral centers. 3 sites correct, 1 site wrong. Here or here or here. Those are the main byproducts. The others are too small to be concerned. Okay, then we learn that as soon as we see this yellow box, 1-hydroxy-2,4-dimethyl-1-hydroxybutyl, yellow box, pretty much regardless of what we have on outside, you can just chromatographically purify this yellow box. So this is pure. Now, as I was telling you, we do copper catalyzed alkyl coupling here of essentially coaches, maybe. Wonderful reaction. We cannot compete with this thing with a palladium catalyst, believe me. So we methylate, and now we deprotect, and then do the same. And after 2 oxidation, we are here. Okay? So now I realize I'm running out of time. As I run out of time, I will show you that this method has become better and better and better. Here is the example of bromoboration of alkyne that I was telling you, Michael Appert. And now we can synthesize all kinds of compounds of these structure with a very, very feeble chirality. In other words, methyl here and methyl here. So methyl and ethyl, methyl propyl or ethyl propyl, propyl butyl. Doesn't matter. Actually, if you synthesize them by the same Zaka reaction and then purify, then you will have various degrees of difficulties. But look what we do. We do a Zaka reaction and we make this one, and we purify these heavily functionalized intermediate, very pure, greater than 99% E. That's very easy. Lipase catalyzed acetylation. Then always there's cross-coupling waiting. Doesn't mess up anything. Just snap 2 pieces together, then you get a pure one. But now, in some cases, their chirality is so feeble that we cannot even tell by Morsha ester analysis. So we now in the process of finding a better analytical method. Well, thank you very much. This is my story, and I thank all these 100+ people who have developed palladium catalyzed cross-coupling. While Dave Van Horn, he was the most talented, despite his wild nature, most talented graduate student. And Dennis Kondakov, nothing wild about him. Probably the best postdoc that I have ever had. Thanks to him, we found this reaction. Recent photos, predominantly dominated by people from China. Thank you.
Thank you very much, Professor Negishi, for introducing us the significance and the beauty of the organometallic chemistry involving very recent results that Zaka reaction, the alphos say Zak asymmetric center. Okay, whatever. Now the session is open for discussion. So, do you have any questions and comments? Please.
My name is Toshaharu Noji from Japan. My question is, what is the most important to get new concept, new like a Negishi cross coupling?
Sorry, I missed the key word. What is the most
important thing?
Important
Thing.
Thinking, thought in cross coupling?
To get new new concept.
Yeah. Well, first of all, to have this Lego game thing, that's of course the cross coupling, and beyond that, I found how how limited the Grignard chemistry was. Then that led me to seek some catalyst, and I would say what was most important to me was to recognize that we only get to use 70 elements, and of which about 60 are metals, and of which probably 20 or so can serve as a wonderful catalyst. So I started doing what I call periodic table walking on the periodic table. So I started with a boron and copper. Yeah, boron and copper. Boron and copper catalyst. Nothing worked for us. And then came Tamao's nickel catalyzed Grignard reaction. So I said, maybe boron and nickel. Is this a crazy idea? But why not? We tried. It didn't work. Okay, the nickel and boron didn't work. Finally, I gave up on Professor Brown's boron. I wanted to make a boron chemistry more widely usable. Then of course, that the boron, aluminum, gallium, indium, thallium. So we shifted from boron to aluminum. Bingo! 1976. It was a major discovery for us, probably for the community as well. Okay, as soon as I found aluminum, then, of course, there's a zinc nearby. Well, at that time, I screened the 10 or so main group metal. You screen. It takes only 2 weeks. And out came zinc. So zinc popped up. And what else? That's how. Yeah. Oh, so sorry. I haven't reached palladium yet. When we came to zinc and nickel, then I said, well, let's screen nickel, palladium, platinum, the triad. Mendeleev told us they are there. So we screened those three. Palladium popped up. More reactive, much more selective, and palladium has ever since been the main catalyst metal. So this kind of playing with periodic table or playing within your ballpark, using the whole ballpark. It's very simple. Okay?
Thank you.
Okay, so any other questions, comments? So, okay, please.
Thank you very much for an interesting talk. My name is Saya Takeuchi. I'm from Kyoto, Japan. My question will be very general question. I believe you have left your company in Japan and took a scholarship to go to the States. And I believe you could have really safe life in Japan. But what made you to be so bold and take the chance by yourself, and you have achieved so many brilliant things, and what made you to do so? What was your main for
Okay.
to achieve that?
Nobel Prize, I'm not sure, but I can tell you a few things early on. So when I graduated from University of Tokyo, this polymer industry was booming. They were recruiting for each of us. They said, people said that there are 8 to 10 companies in those areas. They are wanting each of us to come. So no problem. I went to Teijin. I was assigned in a research lab, and then one of my superiors told me, well, I want you to begin systematic investigation of chemical reactions of a polymer. Polymer may be a cellulosic polymer. They wanted to, derivatize, chemically react, and come up with acetate, which they did, of course, in Europe maybe, and so on. They wanted to have other, better products. Then I said, what? How do I begin to begin? I mean, how do I approach this? My knowledge of chemistry, organic chemistry, especially laboratory, skill, were next to nothing. So I immediately thought of going back to school for master's degree, maybe PhD degree, and come back. But I then realized that you need tuition money, which my family couldn't pay. Then I remember that the president of the company, famous person, in welcoming speech, they said, "Oh, you young people, go abroad." It's interesting. As soon as they hired us, the president would say, "Go abroad." Of course, on leave of absence. Now I hear that there's a Fulbright scholarship. If you win that one, we will give a little extra support on leave of absence. You go, And in fact, that company ended up sending at least several Fulbright scholars. And they hired an English-speaking tutor, and our practical English got better and better. Problem was, as I was telling you, success ratio was 1 in somewhere anywhere from 50 to 100. That was the toughest test that I have ever taken in my life. But luckily I won. That's how I went. I was so eager to go abroad, contrary to some of you or many of you. But I was just engaged to my wife, so we accelerated our wedding, and then I went alone. It took me half a year to bring her over to Philadelphia, but whole thing worked out okay. So that's how. And what I saw in America back in 1960, wow, that was amazing. And every other month, Nobel Prize winners would come give a lecture. Many famous ones, Kendrew and Perut, and I'm not sure if I heard Crick Watson, but Pauling and so on. And others who I thought were destined to win Nobel Prize. Woodward and H.C. Brown was one of them. So when I heard him speak in 1962 on his discovery of hydroboration and further development, I said, this is it, organometallic chemistry, 10 plus 60. So that's how I chose him, and I went to Purdue. That's how.
Thank you. Okay, please.
Thank you very much for your great lecture. As you mentioned at the beginning, you are going to use the carbon dioxide, CO2.
Yes,
Yeah. In organic chemistry reaction in a catalytic way. So my question is, have you made any progress till now? And is it possible for you to share with us some secrets? Thank you.
No, we haven't. We have not yet achieved the kinds of catalytic reduction that we like to have. Okay, but some other plans, since they are paper chemistry, I'd like to keep within my pocket. There are so many eyes, so many ears, maybe too many. But I was presenting this as one of the most highly needed or desirable, sought after plans. Okay, so we all should consider.
Okay, so the thing is, time is limited, so I'm afraid I have to close this session. So before closing, so please join me to thank Professor Negishi again.
Well, thank you very much.
Any announcement?